Welcome to The Blueprint of Emergence, a structural and mathematical guide to agent-based modeling in complex systems. Agent-based modeling, or ABM, is a modeling architecture, not a single equation. It is a bottom-up approach where autonomous entities act on local rules, allowing the global pattern to emerge, unlike top-down conservation laws. The anatomy of an agent involves its current state, its neighborhood, the environment, and noise, which all feed into an update rule to determine the agent's new state. The overall microscopic state is a collection of these individual realities. The stochastic bridge connects discrete microscopic rules to continuous probabilities. A transition kernel governs the movement from one microscopic configuration to the next, evolving the probability distribution over time. ABMs operate microscopically, but we generate macroscopic observables from the bottom up. Spatial fields and order parameters, like density and polarization, are defined directly from the states of individual agents. Within the computational ecosystem, ABM stands out. Its fundamental unit is the autonomous agent, driven by local behavior rules. Its key strength is its ability to capture heterogeneity and emergent behaviors. Physics needs ABMs for their non-equilibrium advantage, particularly in active matter. ABMs naturally encode persistent forcing, local memory, communication, and heterogeneous interactions, allowing us to discover mechanisms before deriving continuum theory. A canonical physics example is the Vitsec model for flocking. Trivial local rules, such as alignment with neighbors and a noise term, generate non-trivial global order. The Vitsec model provides a clean demonstration of emergent symmetry breaking. Starting from disordered motion, local clustering eventually leads to coherent flocking, where the order parameter approaches 1. Continuous time ABMs, like active Brownian particles, are written as stochastic differential equations. They include self-propulsion, interaction potential, and translational noise, modeling phenomena like clustering and motility-induced phase separation. In materials science, ABM captures discrete realities, such as modeling heterogeneity, irregular local neighborhoods, and history dependence. It is a complementary approach for materials where discrete units reshape the bulk material. Agent-based modeling offers two lenses under one architecture: the pursuit of emergence in physics and the capture of heterogeneity in materials science. The key takeaway remains: specify the local rules and let the global pattern emerge. Welcome to Engineering Emergence, a strategic guide to agent-based modeling, or ABM, in the physical sciences. Physics often uses a top-down view with mean field equations describing macroscopic averages. However, this ignores individual material heterogeneity. The bottom-up framework of ABM, in contrast, uses local stochastic rules to explain large-scale regularities, testing mechanisms, and generating synthetic data. The continuum approach has blind spots. Classical mean field laws describe pure averages, but cannot account for specific, localized heterogeneities that dictate real-world material failure or growth. This includes pinned boundaries, anisotropic mobility, and local impurities. Agent-based modeling translates physical concepts, like curvature, into local rules. An agent, with its identity and orientation, follows a rule defined by mobility, energy, and curvature. This leads to local moves, such as retraction, shrinking, or neighbors absorbing territory. Global distributions emerge naturally, without top-down instructions. ABM enables encoding valence and binding at the mesoscale. Mesoscopic particles are the actual assembling units. Stochastic graph building exposes hidden nucleation pathways, kinetic traps, and defect rates that mean field approaches often obscure. Degradation can be modeled as a competing state machine, with states like passive, active, pit, and healed. The probability of transitioning to an active state depends on localized factors. This allows corrosion to be modeled as a competition among local sites driven by spatial heterogeneity and stochastic initiation. The engine of ABM often involves coupling agents to the continuum. Upward coupling means the environment dictates the agent, while downward coupling means the agent alters the environment. This is useful for applications like particles moving in concentration gradients or localized corrosion in electrolyte fields. The ABM advantage rests on 5 pillars of physical utility: heterogeneity, discrete reality, nonlinear rules, emergence from local interactions, and capturing fluctuations in distributions. However, ABM has weaknesses. Rule arbitrariness is a major danger, where plausible local rules might not represent actual physics. Other traps include parameter explosion, difficulty in calibrating models to experimental reality, coarse graining difficulty, and high computational cost. ABM is not always the best tool. For electronic structure, atomistic dynamics, or bulk stress, other methodologies like DFT, MD, or FEM are superior. ABM is the exclusive choice when heterogeneous entities, local information flow, and emergence dictate system behavior. ABM occupies the mesoscale niche, bridging the gap between event kinetic and macroscopic approaches. It excels where heterogeneity and local information flow create macroscopic phenomena. A diagnostic checklist helps determine if ABM is required. Strong use cases include systems with distinct, discrete objects, critical heterogeneity and fluctuations, and where the core question is micro to macro emergence. Weak cases involve reliable continuum equations or purely atomistic physics. ABM and continuum approaches are different scales of description. In physics, ABM dominates non-equilibrium systems and pattern formation. ABM is most valuable when discreteness, heterogeneity, local interaction rules, and emergence matter more than closed-form continuum equations.